In the grand, silent theatre of the cosmos, there is one absolute, unchanging constant. It is a law woven into the very fabric of existence, a universal speed limit. This immutable velocity is the pace of light itself. It is the swiftness of a photon, born in the heart of a colossal star as it embarks upon a solitary journey across unimaginable voids. For millions of years, it travels, a ghost of pure energy, witnessing the birth and death of galaxies in its silent passage. Finally, its epic voyage concludes, ending its existence on the retina of a human eye, delivering a final, faint message from a long-dead sun. This cosmic messenger travels at approximately 299,792 kilometers per second. It is a velocity so extreme, so far beyond our terrestrial experience, that it defies our intuition and challenges our imagination. It is a speed that could circle our entire planet more than 7 times in a single second. This is not merely a benchmark of quickness, it is the fundamental tempo of reality, and it presents humanity with a profound and perhaps eternal barrier, an ultimate frontier we can approach, but one we may never, ever cross. The story of why this is so is not just a tale of physics and mathematics. It is a narrative about our own limitations and our boundless ambition. Since the dawn of consciousness, our species has been obsessed with motion. Our earliest ancestors measured their world in the pace of their own 2 feet, their survival dependent on their ability to outrun predators or pursue prey. The first great leap was not of intellect alone, but of speed. The domestication of the horse granted us a velocity that transformed societies, enabling the creation of sprawling empires and the exchange of distant cultures. We were no longer bound by the rhythm of our own muscles. The invention of the wheel was another monumental step, a testament to our ingenuity in overcoming the friction of the world. For millennia, this was the pinnacle of human swiftness. The world moved at the speed of a galloping horse or a wind-filled sail. Philosophers and thinkers of the ancient world, from Athens to Alexandria, contemplated the nature of motion, but they had no reason to conceive of a limit. To them, speed was purely relative. An object was fast only in comparison to another. It seemed logical that if you simply applied more force, you would always gain more speed. There was no ceiling, no ultimate barrier in their conception of the physical world. This intuitive idea became the bedrock of classical mechanics. Centuries later, the great Sir Isaac Newton would formalize these concepts. In his grand clockwork universe, space was a static, absolute stage, and time was a universal river, flowing at the same rate for everyone, everywhere. His laws of motion were elegant and, for the world he could observe, perfect. They described the fall of an apple and the orbit of the moon with equal precision. In Newton's cosmos, if you were on a train moving at 100 kilometers per hour and you threw a ball forward at 20 kilometers per hour, its speed relative to the ground would be a simple sum 120. This additive nature of velocity was common sense. It was reality. And so, we built our world upon this Newtonian foundation. The Industrial Revolution was, in essence, a revolution in speed. Steam engines, thundering along iron rails, compressed geography and time. Great steamships turned oceans into predictable highways. Humanity was accelerating, shrinking its own planet with each new invention. By the turn of the 20th century, we had automobiles breaking land speed records, and the dream of flight was just on the horizon. Our thirst for greater velocity seemed unquenchable, and physics gave us no reason to doubt. The cosmos, it appeared, placed no restrictions on our ambition. But deep within the elegant mathematics of another field of physics, a strange paradox was lurking. In the mid-19th century, the brilliant Scottish physicist James Clerk Maxwell had unified the disparate phenomena of electricity, magnetism, and light. He produced a set of 4 beautiful equations that described how these forces behaved. His work was a triumph, one of the greatest intellectual achievements in human history. But buried within his elegant formulas was a deeply troubling, almost heretical, number. The equations predicted that light as an electromagnetic wave must always travel at a very specific speed, a value he calculated to be astonishingly close to the already measured speed of light. The problem was, his equations gave no quarter. This speed was not relative to anything, it was absolute. It did not matter if you were running towards the light source or away from it. According to Maxwell's infallible mathematics, you would always measure its velocity as being the exact same, unchanging value. This flew in the face of all experience, of all Newtonian logic. It was as if that train from our earlier thought experiment switched on its headlamp, and the light from that lamp would travel away at the speed of light, not the speed of light plus the speed of the train. This was a logical impossibility, a crack in the very foundation of physics. For decades, the scientific community wrestled with this profound contradiction. They proposed strange theories to resolve it, such as the existence of a luminiferous ether, an invisible, undetectable medium that filled all of space, through which light waves propagated. But every experiment designed to detect this ether, to measure Earth's motion through it, failed. Physics was at a standstill, caught between the unimpeachable success of Newton's laws and the baffling, contradictory elegance of Maxwell's equations. The universe, it seemed, was playing by two different sets of rules. The resolution would come not from a grand university or a state-funded laboratory, but from the mind of a young clerk working in the Swiss patent office in Bern. Albert Einstein, a man whose genius was his ability to question the most basic assumptions, spent his days reviewing patent applications for electromagnetic devices. In his spare time, he pondered the deep inconsistencies that troubled the world of physics. He began with a simple, yet revolutionary, thought experiment. What would the universe look like if you could ride alongside a beam of light? Newtonian physics suggested you would see a static, frozen electromagnetic wave next to you. But Maxwell's equations made this impossible. Such a thing could not exist. Einstein decided to take a radical leap of faith. He proposed that Maxwell's equations were correct. The speed of light is constant for all observers. And if that were true, then the things we assume to be constant space and time must be flexible. They must stretch and shrink in order to conspire to keep the speed of light the same for everyone. This was the heart of his 1905 paper on the special theory of relativity, a work that would shatter the Newtonian worldview and redefine our understanding of the cosmos. It was an idea so counterintuitive, so contrary to our lived experience, that it remains one of the most difficult concepts for the human mind to grasp. To visualize this, imagine the universe is a vast cosmic ocean. The laws of physics are the rules governing how things move through this ocean. In the old Newtonian view, you are in a boat. If you are still, and another boat passes you at 10 knots, you measure its speed as 10 knots. If you start moving at 5 knots in the same direction, that same boat now seems to be passing you at only 5 knots. Its relative speed has changed. This is intuitive. Now, imagine there is a special, magical wave in this ocean, a light wave. Relativity states that no matter how fast your boat is going, or in what direction, when you measure the speed of this magical wave, you will always get the exact same answer. How can this be possible? How can a wave move away from you at the same speed, whether you are chasing it or running from it? Einstein's brilliant insight was that the universe must perform a kind of accounting trick. To keep the speed of light constant, it must alter the very measurements you use. It must change the length of your ruler and the ticking rate of your clock. As your boat speeds up through this cosmic ocean, your vessel begins to physically contract in the direction of motion. Simultaneously, time for you aboard the boat begins to slow down. These effects are imperceptible at everyday speeds, but as you approach the velocity of light, they become dramatic and eventually overwhelming. This brings us to the first great wall preventing us from reaching light speed, mass, and energy. In another of his miraculous papers from 1905, Einstein derived the most famous equation in history, E equals mc squared. This simple statement revealed a profound and previously unknown truth about the universe. It declared that energy and mass are not separate things. They are two different manifestations of the same fundamental substance. Mass is a fantastically concentrated form of energy, and energy has mass. This equivalence is the key to understanding why reaching light speed is an impossibility for any object with mass. When you push on an object, you are giving it kinetic energy, the energy of motion. According to Newton, if you keep pushing, it will keep accelerating indefinitely. But Einstein's relativity shows us something far stranger happens. As you pump more and more energy into an object to make it move faster, that added energy contributes to the object's total mass. Its relativistic mass begins to increase. At first, the increase is minuscule, too small to notice, but as you get closer and closer to the speed of light, the effect snowballs. The object becomes heavier and heavier, more and more resistant to further acceleration. Imagine you are trying to push a child on a swing. At first, a gentle nudge is all it takes to get them going. Now, imagine that with every push, the child gets slightly heavier. As they swing faster and faster, they become more and more massive. Soon, you are pushing with all your might just to add a tiny fraction more speed. Now, imagine that, as the swing approaches its maximum possible height, the child's mass begins to increase exponentially towards infinity. You could summon all the strength in the world, push with the force of a rocket engine, and you would only succeed in making the child infinitesimally heavier, nudging them an imperceptible distance closer to that final height. This is precisely what happens as an object with mass approaches the speed of light. Its mass curves upwards on a graph, heading towards an infinite value. To accelerate an object that has infinite mass would require an infinite amount of energy. And since there is not an infinite amount of energy in the entire observable universe, it is a physical impossibility for anything with even a single speck of mass to be accelerated to the full speed of light. The speed of light is a cosmic asymptote, a finish line you can forever approach, but are fundamentally forbidden from ever reaching. Photons, the particles of light, can travel at this speed only because they are massless. We, and the starships we dream of, are not. But let us, for a moment, indulge in fantasy. Let us imagine we could somehow acquire a near-infinite source of energy. Perhaps we have learned to harness the power of black holes or annihilate matter with perfect efficiency. Even with this godlike power, the universe erects other, equally formidable barriers that would make near-light-speed travel a truly hellish experience for any human crew. The first of these is the problem of the interstellar medium. We often think of space as being perfectly empty, a pure vacuum. This is not entirely true. The void between the stars is sparsely populated, with stray atoms, mostly hydrogen, and tiny grains of dust. At the speeds we currently travel, these particles are utterly inconsequential, but at relativistic velocities, they become lethal projectiles. A spaceship traveling at 99.9% the speed of light is moving so fast that from its perspective, these stationary particles are slamming into it at 99.9% the speed of light. At these energies, a single grain of sand, no bigger than a millimeter across, would impact with the kinetic energy of a large atomic bomb. Even a single hydrogen atom, the most common element in the universe, becomes a bolt of high-energy radiation upon impact. The ship would be bombarded by a constant, unceasing storm of these particle strikes, each one a tiny explosion, collectively eroding the hull and irradiating everything inside. To survive this, cosmic sandblasting would require a shield of unimaginable strength and thickness. This shield would, of course, add immense mass to the ship, which in turn would exponentially increase the already infinite energy requirements. It is a vicious, inescapable cycle. The solution to one impossible problem only serves to make another impossible problem even worse. And it is not just stray particles that become a threat. The very light from the stars ahead of you would be transformed into a weapon. As you rush towards a star, its light waves become compressed, their frequency shifted towards the high-energy end of the electromagnetic spectrum. This is called blue shifting. At extreme relativistic speeds, The gentle, visible light from a distant star would be blue shifted into deadly high-frequency X-rays and gamma rays. The front of your ship would be facing a torrent of sterilizing radiation pouring forth from what appears to be a single, terrifyingly bright point in the sky. Simultaneously, the ancient, cold background radiation of the universe, the faint microwave afterglow of the Big Bang, would itself be shifted into an intense, high-energy bath. Your ship would essentially be flying through the heart of a particle accelerator, cooked from all sides by the very fabric of space-time. Yet, even if we could solve the energy problem and the shielding problem, relativity presents us with a final, deeply personal, and perhaps most tragic barrier, the phenomenon known as time dilation. Einstein showed that just as space contracts at high speeds, time dilates or slows down. The faster you move through space, the slower you move through time. This is not a trick of perception. It is a fundamental property of the universe. Atomic clocks on GPS satellites, which orbit the Earth at high speed, must be constantly corrected for this effect, or our navigation systems would fail within hours. For a spaceship traveling at near the speed of light, this effect would be profound. Imagine a mission to our nearest star system, Alpha Centauri, about 4.3 light-years away. Aboard a ship traveling at 99.5% of the speed of light, the journey from the crew's perspective would take only about half a year. They would arrive, explore, and begin their journey home, experiencing a total mission time of perhaps 2 or 3 years. But upon their return to Earth, they would be greeted by a world they no longer recognized. Because while only a few years had passed for them, hurtling through the cosmos, back on Earth, nearly a decade would have gone by. Their friends and family would be older, the world changed. Now, consider a journey to the center of our own Milky Way galaxy, a distance of some 25,000 light-years, for a crew aboard a sufficiently advanced starship, accelerating to a velocity just shy of light speed. The journey could be completed in a matter of decades from their point of view. They could live out a normal lifespan and witness the majestic heart of our galaxy. But when they returned, if they returned, they would find that 50,000 years had elapsed on Earth. Everyone they had ever known would be gone. Every nation, culture, and language they remembered would be dust and myth. Humanity itself might have evolved into a different species, or vanished entirely. They would be aliens on their own home world, ghosts from a forgotten past. This is the ultimate paradox of relativistic travel. It offers the tantalizing prize of the stars, but at the cost of severing all ties to home. To travel near the speed of light is to purchase a one-way ticket to the future. You do not just travel through space, you are catapulted through time. It raises a deeply philosophical question. What is the purpose of a journey if, upon its completion, everything that gave the journey meaning has ceased to exist? It is a form of exile so profound it is difficult to comprehend. The speed of light, in this sense, acts as a great cosmic quarantine, isolating civilizations in their stellar cradles, enforcing a tragic and beautiful loneliness upon the worlds of the galaxy. Faced with these seemingly insurmountable obstacles, does this mean that humanity is forever trapped in its own solar system? That the great dream of interstellar travel is nothing more than a fantasy? Perhaps not. The universe may forbid us from breaking the speed of light, but it might offer loopholes, clever workarounds that could allow for faster-than-light travel, without ever violating Einstein's sacred law. These ideas currently live in the highly speculative realm of theoretical physics, but they represent a profound hope for the future of our species. The most famous of these is the concept of a warp drive. Popularized by science fiction, the idea of a warp drive, or an Alcubierre drive, as it is known in physics, is as elegant as it is mind-boggling. It proposes that instead of trying to move a ship times through time-space at impossible speeds, we could instead move space itself times around times the ship. Imagine space-time as a flat sheet of rubber. Your spaceship is a small marble resting on this sheet. To move the marble, you can push it, but you are limited by the friction of the rubber. This is analogous to being limited by the speed of light. The Alcubierre drive suggests a different method. What if you could pinch the rubber sheet in front of the marble and stretch the rubber sheet behind it, you would create a wave of compressed and expanded space that would carry the marble along. The marble itself would remain perfectly still within its local pocket of space-time, experiencing no acceleration or time dilation. But this bubble of space-time would be moving across the sheet at an arbitrary speed, potentially many times faster than light. This is not magic. It is based on the mathematics of Einstein's general relativity. It is a valid solution to his field equations. However, it comes with a colossal catch. To create this distortion in space-time, to generate the wave, you would need something called exotic matter. This is a hypothetical form of matter that possesses negative mass energy density. To put it simply, it is matter that has anti-gravity. It would weigh less than nothing. While the laws of physics do not strictly forbid the existence of such matter, we have never observed it, and we have no idea how we might create or contain it. It would require rewriting our understanding of quantum mechanics and energy. The warp drive remains a beautiful mathematical possibility, a tantalizing glimpse of what could be if the universe is stranger than we already know. Another potential shortcut through the cosmic distances is the wormhole. Also known as an Einstein-Rosen bridge, a wormhole is a theoretical tunnel through space-time, a topological feature that could connect two very distant points in the universe. Think again of our rubber sheet representing space. To get from one point on the sheet to another, you must travel across the surface. But what if you could fold the sheet over, so the 2 points are touching, and then poke a hole through them, creating a direct passage? This is the essence of a wormhole. You could step through a gateway in our solar system and emerge moments later in the Andromeda galaxy, 2.5 million light-years away. You would not have broken the speed of light locally, you would have simply taken a shortcut. Like the warp drive, wormholes are a valid, if highly unstable, solution in general relativity. The problem is that for a wormhole to be traversable, to be held open long enough for something to pass through, it would also require vast amounts of that same exotic matter. Without it, the tunnel would collapse into a singularity the instant it formed. Furthermore, the gravitational tides near the mouth of a wormhole would be so extreme that they would likely tear any ship and any person apart atom by atom. They remain a fascinating theoretical construct, but a practical means of travel. They are certainly not, at least with any technology we can currently conceive. So, if we cannot break the cosmic speed limit and the loopholes remain purely theoretical, what is the realistic future of humanity's journey to the stars? The most likely answer is also the most challenging. We will have to travel slowly. The future of interstellar colonization may not belong to sleek, warp-capable starships, but to colossal, slow-moving generation ships. These would not be mere vehicles, but self-sustaining worlds in miniature, vast arcs carrying entire ecosystems and thousands of inhabitants. They would accelerate to a small fraction of the speed of light, perhaps 1 or 2%, and then coast through the darkness for centuries, or even millennia. The journey would be the destination. Generations would be born, live their entire lives, and die aboard these world ships, their only purpose to maintain the vessel and its mission for their descendants. They would be a new kind of human, a culture of the deep void, with a sky that never changes and a concept of home that is a distant, legendary memory. The psychological, sociological, and biological challenges of such an undertaking are immense. But it represents a path to the stars that, while daunting, does not require us to break the known laws of physics. It requires only patience and an incredible, multi-generational commitment to a distant goal. In the end, perhaps the speed of light is not a cosmic prison, but a form of cosmic grace. This ultimate speed limit enforces causality, ensuring that effect always follows cause. It creates horizons, vast spheres of influence beyond which we cannot immediately affect or be affected. It gives the universe its structure, its history, and its texture. It forces time to march forward, preventing the chaos of a universe where past and future could mingle. It ensures that localities matter, that stars and galaxies can evolve in relative isolation, creating the incredible diversity we see across the cosmos. Humanity's desire to reach for the stars is one of our most noble aspirations. We look up at the night sky and see not a limit, but an invitation. The speed of light tells us that the journey will be harder and far longer than we ever dreamed. It tells us that we cannot conquer the universe with brute force and velocity alone. We must be cleverer than that. Our destiny may not be to race across the cosmos in the blink of an eye, but to learn, to grow, and to understand our place within this vast and beautiful structure. The ultimate law of the universe is not a barrier to our future, but a challenge to our ingenuity, a call for us to become a species worthy of the long, patient, and magnificent journey that awaits us among the stars. The speed of light is the universe's way of telling us to slow down and to think. Is there any image more serene, more symbolic of our future among the stars than an astronaut asleep? You've seen the footage, broadcast from the silent frontier of human endeavour. A figure, weightless and serene, cocooned within a sleeping bag tethered to the wall of a spacecraft. Their arms drift gently in front of them, unbound by the familiar pull of a mattress. Outside the small porthole, the Earth, a marbled jewel of impossible blue and white, performs its silent, ceaseless pirouette. It is a picture of profound peace, a human being at rest in the cosmos, a dream made manifest. But this tranquility, this placid portrait of slumber in the void, is a beautiful and profound illusion. Behind the closed eyelids of that floating dreamer, a silent, chaotic battle is being waged. It is a war fought not with weapons, but with biology, a rebellion of the body and mind against an environment so alien, so fundamentally wrong, that every instinct screams of a fall that will never end. This is not the gentle surrender to rest that we have known for our entire existence. This is an act of defiance, a forced negotiation with the very laws of nature. To truly understand the monumental challenge of sleeping in space, we must first return to Earth. We must unravel the deep unspoken contract we have with the planet beneath our feet, a contract written in the language of gravity. For us, sleep is not merely a state of unconsciousness. It is an act of surrender to this invisible, ever-present force. Think of it. From the moment you were born, every night of your life has been defined by the simple, comforting act of lying down. That sensation, the gentle but firm pressure of a surface against your back, your side, your front, is the first and most primal signal to your body that it is time for rest. It is a message of safety, of stability. Gravity provides the anchor, the fundamental orientation of your world. There is a down, a direction of surrender, and an up, a direction of striving. When you close your eyes, your mind doesn't have to wonder where the floor is. Your inner ear, a sophisticated gravitational gyroscope filled with tiny, delicate crystals, constantly reports your orientation to your brain, confirming that you are secure, horizontal, and at peace. This constant, reassuring signal is the silent lullaby of our world. This gravitational cradle does more than just hold us. It orchestrates a complex ballet within our bodies. As you lie down, gravity pulls the fluids in your system downwards, away from your head, relieving pressure and allowing your cardiovascular system to enter a lower gear. Your muscles, which have spent the entire day fighting a 1G war just to keep you upright, are finally granted a reprieve. They can relax, repair, and release the tension of the day because gravity is no longer demanding their constant service. Every cell in your body is attuned to this rhythm, this daily cycle of resistance and release. Our sleep architecture, the intricate dance between light sleep, deep sleep, and REM, has been sculpted over 3.5 billion years of life on this planet, all of it unfolding under the steady hand of Earth's gravitational field. We are, in the most literal sense, creatures of the downward pull. We take it for granted, this foundational comfort, as we do the air we breathe. It is the invisible constant against which the entire drama of our lives, both waking and sleeping, has been set. We are so exquisitely adapted to it that we never even notice its presence, until it is gone. Now, imagine we strip all of it away. In an instant you are transported to orbit, to that place of seeming tranquility. The first thing you lose is not your weight, but your orientation. The very concept of down ceases to exist. There is no floor to fall towards, no ceiling to rise from. Every direction is identical, a bewildering expanse of sameness. Your inner ear, the sophisticated biological instrument that has guided you and your ancestors for millennia, is thrown into utter chaos. The tiny otoliths, those crystalline stones that tell your brain which way is down, begin to float freely, sending a constant stream of nonsensical, contradictory signals. The brain, receiving this flood of gibberish, believes you are tumbling, falling, spinning, and standing still, all at the same time. It is a state of perpetual vertigo, a neurological storm that for many astronauts persists for days, a condition politely known as space adaptation syndrome. You are forever falling, yet you never land. How can a mind possibly surrender to sleep when its most ancient sensory system is screaming that it is in constant mortal peril? The physical rebellion is just as profound. Without gravity to pull them down, the fluids in your body, blood, lymph, the water in your very cells, begin to shift. They migrate upwards into your torso, your neck, and your head. Astronauts often describe the immediate sensation of a stuffy nose, a congested head, and a persistent dull headache, as if they were trying to sleep while hanging upside down. Their faces become puffy and swollen. This fluid shift doesn't just create discomfort, it fundamentally alters the body's internal pressures. The heart, confused by the increased fluid volume in the upper body, initially believes the body is overhydrated and signals the kidneys to excrete more water, leading to dehydration. The pressure inside the skull increases, a dangerous condition that can even affect an astronaut's vision over long-duration missions. The body is in a state of crisis, desperately trying to recalibrate its most basic functions to a reality it was never designed to encounter. This is the physiological landscape upon which an astronaut must attempt to build a sanctuary of rest. And then there is the simple, yet profound, absence of contact. The comforting, grounding pressure of a bed is gone. You are floating, untethered from any tactile sense of security. To solve this, astronauts don't sleep in beds. They zip themselves into sleeping bags that are strapped to a wall, a ceiling, or a floor. Though these terms are now merely conventions of language, they must secure themselves tightly to prevent their unconscious bodies from drifting around the cabin, bumping into delicate equipment or other crew members. Yet even this solution is an imperfect substitute for gravity's embrace. There is no sensation of weight sinking into a mattress, no feeling of being held. Many astronauts report that their arms, lacking the downward pull they are accustomed to, float up in front of their faces as they fall asleep, a disquieting and often disturbing phenomenon sometimes called zombie hands. They are forced to tuck their arms inside the sleeping bag to prevent this spectral wandering. They are physically restrained, yet sensorially adrift in a way we can barely comprehend. This physical and neurological disorientation is compounded by an environment that is anything but peaceful. A space station is not a silent cathedral in the void. It is a complex, living machine. It hums, it whirs, it clicks. Fans circulate the very air you breathe. Pumps cycle coolant to regulate temperature. Life support systems, the mechanical heart and lungs of your orbital home, are in constant operation. There is no true silence, only the ceaseless, low-level drone of the technology that keeps you alive. It is a constant, unavoidable roommate. Furthermore, the celestial clock that governs our lives on Earth is gone. Aboard the International Space Station, astronauts experience a sunrise or a sunset every 45 minutes. They orbit the Earth 16 times a day, witnessing 16 sunrises and 16 sunsets. The delicate circadian rhythm, our internal 24-hour clock that has been meticulously synchronized to Earth's rotation for eons, is immediately severed from its primary external cue. The fundamental cycle of light and dark that tells our brains when to produce melatonin, when to feel drowsy and when to be alert, is replaced by a dizzying artificial strobe effect. Scientists and engineers, of course, are acutely aware of this. They are the architects of artificial rest. They attempt to impose an earthly rhythm on this unearthly place. They schedule a strict 24-hour day, with designated work periods, meal times, and an 8-hour block reserved for sleep. They dim the lights inside the station to simulate nightfall, creating a synthetic twilight in the heart of the machine. They even use specialized lighting systems with different color temperatures, mimicking the blue-rich light of morning to promote wakefulness and the warmer red-shifted light of evening to encourage sleep. But these are engineered solutions to a deeply biological problem. You can dim the lights inside, but you cannot stop the sun from blazing through a porthole at what is supposed to be 3 o'clock in the morning. An astronaut might be trying to sleep, following the mission clock, while the brilliant light of the Earth, a phenomenon known as Earthshine, illuminates their cabin with an ethereal glow. They are living on a manufactured schedule, a fragile human construct superimposed upon a cosmic reality that operates on an entirely different timescale. The psychological toll of this struggle for rest cannot be overstated. Sleep is the mind's great restorative process. It is when we consolidate memories, process emotions, and solve problems. When sleep is fragmented, shallow, and unrefreshing, as it so often is in space, the consequences can be severe. Astronauts often report vivid, intense, and sometimes bizarre dreams, perhaps the mind's way of trying to make sense of its bizarre new physical reality. They also face a unique form of anxiety. Here you are, floating in the most isolated, dangerous environment humanity has ever inhabited. Your life, and the lives of your crewmates, depend on your absolute peak cognitive performance. A single miscalculation, a moment of sluggishness, a delayed reaction to an alarm could have catastrophic consequences. The pressure to perform is immense, and that pressure is a known enemy of sleep. You lie there, strapped to a wall, listening to the hum of the station, feeling the pressure in your head, acutely aware that a good night's sleep is not a luxury, but a critical component of your own survival. This creates a vicious cycle. The anxiety about not sleeping becomes the very thing that prevents you from sleeping. This is why the seemingly simple question, "How do astronauts sleep?" is one of the most critical and complex challenges in human spaceflight. It is not a matter of comfort or convenience. It is a fundamental pillar of mission success and crew safety. We have learned through painful experience that sleep deprivation is as debilitating as any illness. It impairs judgment, slows reaction time, degrades problem-solving abilities, and can lead to serious errors. On Earth, a drowsy driver is a danger. In space, a drowsy astronaut is a potential catastrophe, piloting a multi-billion-dollar vessel at over 17,000 miles per hour, where the margin for error is non-existent. As we set our sights on longer and more ambitious missions, to the Moon, to Mars and beyond, journeys that will take astronauts away from the cradle of Earth for years at a time, solving the problem of sleep becomes paramount. We cannot send human beings on these epic voyages only for them to arrive at their destination exhausted, cognitively impaired, and unable to perform the very tasks they were sent to do. The human body must be able to find genuine, restorative rest in the void if we are ever to truly become a multiplanetary species. So, the image of the peacefully floating astronaut is not the end of the story, but the very beginning of our investigation. It is a question mark hanging in the silence of space. How do we trick the body into believing it is safe when every signal tells it that it's falling? How do we untangle the neurological knots tied by the absence of up and down and coax the brain into the deep healing states of slumber? We must dive deeper into the physiological war being waged within the circulatory, vestibular, and nervous systems, exploring the microscopic battles that define an astronaut's night. We need to enter the psychological landscape to understand the dreams and anxieties of a mind unmoored from its planetary home. And finally, we must examine the remarkable ingenuity, the sheer engineering brilliance required to build a bedroom at the edge of the abyss. This is a story about more than just sleeping bags and eye masks. It is a story about a fundamental clash between our terrestrial biology and our cosmic ambition. It is the quest to find a moment of true peace, a genuine good night, in a place where the rules of night and day have been completely rewritten. The journey to the stars, it turns out, depends utterly on mastering the simple, yet elusive act of falling asleep. What happens when you take away the night? Not just the darkness, which can be conjured with a simple shade, but the very essence of it. What becomes of slumber when you remove the fundamental pillar upon which it is built? We think of sleep as a surrender, a letting go, a gentle fall into unconsciousness. Every night of your life you have performed this act of faith, trusting in a force you never see to hold you, to cradle you, to define the very meaning of rest. That force is gravity. It is the silent partner in every dream you have ever had, the invisible anchor that moors your body to your bed, allowing your mind to drift. But humanity was destined to leave its cradle, to venture into an endless ocean where the concepts of up and down dissolve into meaninglessness. Out there, in the silent, star-dusted void, a question that had never before needed asking suddenly became one of the most vital, complex and intimate challenges of survival. How do you fall asleep when there is no direction in which to fall? This was not a problem of engineering, not at first. It was a profound biological and psychological riddle, a confrontation with an environment so alien it threatened to unravel the most ancient rhythms of human life. The quest to conquer space was, in its quietest moments, a quest to simply find a way to close one's eyes and find peace in a place that offered none. The first forays into the cosmos were breathtaking sprints, too short for the creeping exhaustion of true sleep deprivation to take hold. Yuri Gagarin's single orbit, a glorious 90-minute blaze of history, was an exercise in pure, unadulterated wakefulness. The pioneering American Mercury astronauts, strapped into capsules barely larger than their own bodies, were focused on control, on survival, on the sheer overwhelming experience of seeing the world unspool beneath them like a divine tapestry. Sleep was a luxury for a future they were only just beginning to imagine. Yet, the question lingered in the minds of the flight surgeons and mission planners. They knew that to truly live in space we would have to learn to rest there. The first human to truly confront this challenge was German Titov, the second Soviet to orbit the Earth. His Vostok 2 mission was designed to last a full day, a crucial test of whether a human being could endure the void for an extended period, and for the first time, sleep was officially on the flight plan. When the designated time came, Titov dutifully prepared for his historic slumber. He was a cosmonaut, the epitome of discipline and control, yet, as he attempted to drift off, the universe itself seemed to conspire against him. The absence of gravity, this new and thrilling freedom, became a kind of sensory torment. His inner ear, the delicate fluid-filled gyroscope that had oriented him his entire life, was utterly bewildered. Without the constant pull of Earth, it sent a cascade of confusing signals to his brain, creating a dizzying, nauseating sensation that would come to be known as space adaptation syndrome. The gentle pressure of his head on a pillow, the subtle weight of a blanket. These were sensations his body had used for decades as cues for rest. Now there was nothing. His head floated uncomfortably and his arms drifted upwards in front of his face, a phenomenon the astronauts would later call the chicken wing pose, as if perpetually ready to embrace a phantom. Titov's slumber was fitful, nightmarish, punctuated by disorientation. He slept, but he did not rest. His experience was the first critical data point in a brand new science, a stark warning that leaving the planet meant leaving behind more than just the ground. We were leaving behind the very definition of repose. The problem came into sharp, agonizing focus during the Gemini program. These were the missions that forged the path to the moon, two-man crews living in a space no larger than the front seat of a Volkswagen Beetle for days, even weeks on end. Here, sleep was not an experiment, it was a biological imperative. The story of Gemini 7 is a legend in the annals of human endurance. For 14 days, astronauts Frank Borman and Jim Lovell orbited the Earth, pushing the limits of technology and their own sanity. Their mission was to prove that humans could survive in space long enough to fly to the moon and back. A huge part of that proof rested on their ability to sleep. The plan seemed logical enough on paper. One astronaut would sleep while the other monitored the capsule's systems. They would work in shifts, a lonely vigil in the cosmos. But the reality was a sleepless, grinding hell. The Gemini capsule was a cacophony of relentless noise. The constant hum of fans, the whir of electronics, the sharp crackle of the radio transmitting from a world away. There was no night and day, only the spacecraft's own artificial clock and the disorienting 90-minute cycle of brilliant sunshine and abrupt inky darkness as they raced around the planet. Frank Borman, the mission commander, recounted the profound difficulty of surrendering to sleep in such an environment. Without gravity, any position was uncomfortable. They couldn't lie down, they could only float. They tried sleeping in different orientations, wedging themselves against equipment racks, but every muscle seemed to ache with a strange, low-grade tension. Their bodies, evolved for a world of constant gravitational load, were adrift. Borman discovered that if he didn't consciously restrain his head, it would loll forward into a chin-to-chest position that made breathing difficult, a deeply unsettling sensation that would jolt him awake. The sheer mental effort required to stay still enough to sleep was itself exhausting. They were living in a state of perpetual alertness, their nervous systems frayed by the combination of confinement, noise, and the ever-present danger of their mission. Sleep, when it came, was shallow and unsatisfying, more like a series of brief, exhausted blackouts than true, restorative rest. Borman and Lovell returned to Earth as heroes, but they were also spectres of fatigue. Their mission was a resounding success, but it underscored a critical vulnerability. If we were going to conquer the moon, we had to first conquer the simple, universal need for a good night's sleep. The human body could be trained and disciplined, but the brain's demand for rest was non-negotiable. The Apollo missions, for all their grandeur and historic weight, treated sleep more as a necessary inconvenience than a central problem to be solved. The destination was the moon, and the timeline was aggressive. The Apollo Command Module was a palace compared to Gemini, but it was still a cramped utilitarian machine designed for a sprint, not a marathon. The crew of 3 operated on a schedule that was often disrupted by the sheer thrill and intensity of their work. Who could sleep when the lunar surface was growing larger in the window, a grey, pock-marked world of impossible dreams made real? The astronauts developed ad hoc solutions. They used simple restraints, bungee cords, and Velcro straps to anchor themselves, preventing their bodies from drifting into the controls or bumping into their crewmates. They might wedge themselves into a corner, using the slight pressure against the walls to simulate the feeling of being in a bed. Michael Collins, orbiting the moon alone in the command module Columbia, while Neil Armstrong and Buzz Aldrin walked below, described the profound solitude. In the moments he tried to rest, he was acutely aware of being the most isolated human being in history. Sleep was a fragile reprieve, easily shattered by the crackle of a transmission from the lunar surface or the simple, overwhelming thought of his unique position in the cosmos. Yet, the consequences of this accumulated fatigue were deadly serious. The near disaster of Apollo 13 was a testament not only to the ingenuity of the crew and mission control, but also to the dangers of exhaustion. As the crippled spacecraft limped back to Earth, its crew, cold, hungry, and under unimaginable stress, were also profoundly sleep-deprived. Critical calculations, innovative repairs, all were performed by minds pushed to their absolute cognitive limits. Sleep wasn't a luxury. It was a vital resource, as critical as oxygen or fuel. A lapse in judgment born of fatigue could have spelled the end. The Apollo program taught NASA that while you could power a mission with adrenaline and sheer willpower for a few days, a sustained human presence in space would require a fundamental rethinking of how we live and rest among the stars. The answer, when it finally arrived, was not just an engineering solution, it was a psychological breakthrough. It came with America's first space station, a behemoth in the sky that represented a new philosophy of space travel. It was called Skylab. Skylab was a revelation. Constructed from the upper stage of a Saturn V rocket, its cavernous interior workshop felt like a cathedral compared to the closets that had preceded it. For the first time, astronauts had room to move, to work, and to live with a semblance of normalcy. And for the first time, the architects of a space habitat gave serious, dedicated thought to the problem of sleep. They designed what were, in essence, the first true bedrooms in space. Tucked away in a quiet corner of the station were 3 private sleep compartments, small personal pods that offered something utterly revolutionary, a door that could be closed. This simple barrier provided not just acoustic and light insulation, but a profound sense of privacy and personal space that had been impossible in the one-room capsules of the past. Inside each compartment was the real innovation, a sleep restraint system that looked remarkably like a terrestrial sleeping bag. This was no mere sack, however. It was a carefully designed piece of human factors engineering. The bag was mounted vertically against the wall, a visual detail that strikes us as bizarre but was, in orbit, completely irrelevant. In a world with no up or down, sleeping standing up is no different from sleeping lying down. The genius of the Skylab sleeping bag lay in its understanding of the human body's deep-seated needs. It was laced with tensioned straps that the astronaut could tighten, providing a gentle, reassuring pressure all over the body. This pressure was a form of proprioceptive feedback, tricking the brain into feeling secure and grounded, simulating the long-lost sensation of lying on a mattress. It held the head in a neutral position, preventing the uncomfortable forward slump that had plagued Frank Borman. It kept the arms from floating free, containing them within the bag's soft confines. For the astronauts of Skylab, crawling into this vertical cocoon at the end of a long day was a moment of sublime relief. Astronaut William Pogue described his first night as the best sleep he'd had in a long time, on or off the planet. Here, finally, was a sanctuary. By creating a physical anchor in a weightless world, the Skylab designers had provided a psychological one as well. They had proven that with thoughtful design, the disorienting void could be tamed, and the alien environment of space could, in some small way, begin to feel like home. It was a lesson the Soviets, with their own ambitious space station program, were learning and perfecting in parallel. While America was focused on the monumental sprints to the moon, the Soviet Union was quietly playing the long game, methodically building the expertise for permanent human habitation in low Earth orbit. Their Salyut stations, and later the legendary Mir space station, became the proving grounds for long-duration life in space. For the cosmonauts who inhabited these orbital outposts, sleep wasn't just a task on a checklist. It was a fundamental part of a daily routine that could stretch on for months, sometimes over a year. The early challenges faced by pioneers like Alexei Leonov, who conducted the first spacewalk from a primitive Voskhod capsule, gave way to a lived-in, almost mundane reality aboard Mir. Mir was not a pristine laboratory, it was a home. Over its 15 years in orbit, it took on the character of its many inhabitants. The sleep stations, called cayutas, or cabins, were small, private spaces, much like the Skylab compartments. But on Mir, they became intensely personal. Cosmonauts would tape photos of their families to the walls, bring small mementos from home, and listen to music on cassette players before drifting off. These little rituals of personalization were crucial. They were a way of humanizing the cold, mechanical environment, of carving out a small pocket of Earth in the vast emptiness. The Mir sleeping bags were a refined version of the Skylab concept, providing that all-important sense of physical enclosure. Cosmonauts would float into their cabins, zip themselves into their bags and pull a shade over the porthole to block out the searing light of orbital sunrise. Yet, even here, in this most established of space homes, perfect rest remained elusive. Mir was never quiet. Its life support systems produced a constant low-frequency hum that became the soundtrack to life in orbit, a noise that some cosmonauts found comforting, a sign that the station was alive, while others found it an irritating barrier to deep sleep. The air itself, thick with the scent of machinery and the lingering traces of countless science experiments, was a constant reminder of their isolation. But the cosmonauts of Mir demonstrated something profound. They proved that humanity could adapt. They learned to sleep, to dream, and to live for staggering durations in an environment for which they were never designed. They had solved the physical puzzle of how to keep the body from floating away. They had created the first true off-world bedrooms. The journey from the frantic, sleepless nights of Gemini to the routinized slumber aboard Mir was a monumental leap. In just a couple of decades, we had gone from fighting the alien nature of space to creating pockets of familiar comfort within it. We had learned that the human mind needed an anchor, a physical sensation of being held to finally grant the body permission to rest. The sleeping bag, a simple invention, had become a gravitational gyroscope for the soul, yet solving the physical and psychological challenges of where to sleep only opened the door to a deeper, more intricate mystery. What was actually happening inside the mind during this strange floating slumber? Was the sleep they were getting truly the same as the restorative healing process we experience on Earth? The architecture of sleep, the delicate dance between light stages, deep delta wave sleep, and the vivid world of REM, is one of biology's most complex and vital functions. Out there, unbound by Earth's gravity and its familiar 24-hour rhythm, was this ancient biological symphony being thrown into chaos. We had built the bedroom, but we were only just beginning to understand what happened to the dreamer. To truly understand the profound struggle of sleeping in space, we must first journey inward, into the familiar yet mysterious architecture of sleep here on Earth. It is a nightly odyssey we all undertake, a descent into a world governed by rhythms and cycles so ancient, so deeply encoded within our biology, that they feel as fundamental as breathing. For us, sleep is not merely an absence of wakefulness. It is an active, meticulously choreographed performance, a symphony conducted by the silent maestro of time itself. The primary conductor of this symphony resides deep within your brain, a tiny, intricate cluster of about 20,000 neurons known as the suprachiasmatic nucleus, or SCN. Think of it as the master gear in a vast biological clockwork, a timekeeper wound not by hand, but by the rising and setting of the sun. Every morning, as the first photons of dawn stream through our atmosphere and strike the retina at the back of your eye, a signal travels along the optic nerve, not for vision, but for timekeeping. It's a message directly to the SCN, a quiet announcement. The day has begun, reset the clock. This single cue initiates a cascade of hormonal commands that ripple throughout your entire physiology. The SCN signals the adrenal glands to release cortisol, the hormone of alertness, which sharpens your focus, raises your body temperature, and prepares you for the challenges ahead. Simultaneously, it suppresses the pineal gland's production of melatonin, the herald of darkness and rest. For the next 12 to 14 hours, your body hums with the energy of day, all orchestrated by this light-sensitive metronome. But as daylight wanes, the entire process reverses. With the diminishing light, the SCN's alerting signals quiet down. The pineal gland, now unleashed, begins to secrete melatonin into the bloodstream, a gentle chemical lullaby that lowers body temperature, slows metabolic processes, and broadcasts a powerful, pervasive signal to every cell in your body. It is time to prepare for rest. This is the circadian rhythm, a 24-hour cycle of wakefulness and slumber that has governed life on this planet for eons. It is the Earth's rotation, imprinted upon our very DNA. But this grand daily rhythm is only the overture. Once you close your eyes, the true masterpiece begins, a journey through multiple, distinct realms of consciousness, each with its own unique purpose and brain activity. We call these the cycles of non-REM and REM sleep. Your descent begins with stage 1, a fleeting hypnotic state where the boundary between the waking world and the dream world blurs. Your thoughts drift, your muscles begin to relax, and you are easily roused. It's a delicate transition, a gentle letting go of the day. From there, you slip deeper into stage 2 non-REM sleep. Here, your brainwaves begin to slow, punctuated by strange, sudden bursts of electrical activity known as sleep spindles and K-complexes. Scientists believe these are moments when the brain is actively working to consolidate memories, transferring important information from the temporary storage of the hippocampus to the long-term archives of the cortex, a process of neural housekeeping essential for learning. You spend about half of your night in this crucial stage, a workshop where the experiences of the day are sorted, filed, and understood. Then you descend further still into the abyss of stage 3, the coveted slow-wave sleep. This is the most profound state of physical and mental restoration. Your brain produces large, slow, rolling delta waves. Breathing and heart rate drop to their lowest levels of the night. It is in this deep, quiet state that your body performs its most critical repairs. The pituitary gland releases a surge of human growth hormone, mending torn muscle fibers, rebuilding tissues, and bolstering the immune system. This is the realm of true physical recovery, a biological sanctuary without which we would quickly fall apart. After navigating these depths, a remarkable transformation occurs. You ascend not to wakefulness, but into an entirely different mode of being, rapid eye movement, or REM sleep. Suddenly, your brain explodes with activity, becoming as electrically active, and sometimes even more so, than when you're fully awake. Your eyes, though closed, dart back and forth beneath their lids, tracking the phantoms of a vibrant, internally generated world. This is the theatre of the dream, a neurological cinema where the impossible becomes real. Yet while your mind is racing through these vivid narratives, your body's voluntary muscles are almost completely paralyzed, a state known as muscle atonia. This protective mechanism, initiated by the brainstem, prevents you from physically acting out the wild adventures of your dreams. REM sleep is not for the body, but for the mind. It's where we process complex emotions, solve abstract problems, and integrate our experiences into the tapestry of our identity. Throughout the night, you cycle through these stages, from the light doze of stage 1, down to the depths of slow-wave sleep, and back up into the fireworks of REM, approximately every 90 minutes. Each cycle is a perfectly balanced expedition, providing just the right amount of physical repair and psychological processing. But there is a silent partner in this entire intricate dance, a force so constant and pervasive on Earth that we forget it is even there, until it is gone. That partner is gravity. Every night, when you lie down, gravity provides a clear and unambiguous signal to your body. It is the gentle but insistent pressure of the mattress against your back, your head against the pillow. This sensory input, called proprioception, tells your brain precisely where your limbs are in space. It is the fundamental feeling of being supported, of being at rest. Your muscles, sensing this support, receive the cue to fully let go, to release the tension they have held throughout the day, allowing you to sink into the deep relaxation needed for restorative sleep. Gravity also acts as our planet's master plumber for the human body. During the day, it pulls the fluids within you, your blood, your lymph, downward, causing them to pull slightly in your legs and lower torso. When you lie down at night, this gravitational gradient evens out, allowing your circulatory system to function with less effort. Most critically, gravity provides a constant reference point for one of the most delicate and essential navigation systems we possess, the vestibular system, housed within the labyrinth of your inner ear. Within this bony maze are tiny calcium carbonate crystals called otoliths. They rest upon a bed of sensitive hair cells, and as you move your head, gravity's constant pull tumbles these little stones, bending the hairs beneath them. This sends a continuous stream of information to your brain about your orientation, which way is up, which way is down, whether you are accelerating or standing still. Even in the darkest room with your eyes closed, you never lose this fundamental sense of your place in the world. It is your internal gyroscope, your gravitational anchor, and it is so deeply ingrained in your perception that you're not even conscious of its ceaseless input. It is the silent, unwavering foundation of your physical reality. This is the exquisitely tuned machine of terrestrial sleep, perfected over millions of years of evolution on a spinning gravity-bound world. Now imagine we take this perfectly calibrated biological instrument and place it in an environment for which it was never designed. We sever the connection to the 24-hour clock of sunlight and darkness. We remove the comforting pressure of a surface. We silence the constant orienting whisper of gravity. The symphony of sleep does not just become dissonant, it collapses into chaos. The body, unmoored from all its earthly cues, begins to stage a quiet, insidious rebellion against the mind's desire for rest. The first and most immediate assault comes from the body's own internal ocean. Without the familiar downward tug of gravity, the 2 liters of fluid that are normally pooled in your lower body are suddenly liberated. This fluid begins a slow, relentless migration upward, from your legs and abdomen into your chest, neck, and head. Astronauts have a term for the visible result: puffy face, bird legs syndrome. But the cosmetic changes are the least of their worries. This massive fluid shift has profound physiological consequences that directly attack the possibility of sleep. The engorged blood vessels in the nasal passages create a feeling of intense, unrelenting sinus congestion, similar to sleeping with a very bad head cold. Breathing becomes laboured, and the simple act of lying still feels suffocating. More insidiously, this upward tide increases the pressure inside the skull. Your brain, which has spent its entire existence in a carefully regulated pressure environment, is now subjected to a constant, mild increase in intracranial pressure. This can lead to persistent, dull headaches that make relaxation impossible. The optic nerve head can swell, and the very shape of the eyeball can subtly change. In essence, sleeping in microgravity is physiologically equivalent to attempting to sleep on Earth while hanging upside down. The body interprets this constant pressure and congestion not as a state for rest, but as a state of distress, of illness. The fundamental comfort required to initiate sleep is simply gone. While this internal flood wreaks havoc on the body, an even more disorienting battle is being waged within the mind, originating in the inner ear. The vestibular system, your internal gyroscope, is now utterly lost. The tiny otolith crystals which once provided a clear signal of down are now floating freely in the endolymph fluid of the inner ear. They no longer rest on their sensitive hair cells, but drift aimlessly, bumping into them at random, or not at all. The result is a torrent of nonsensical, contradictory data pouring into the brain. Your brain is receiving signals that you are falling, spinning, and standing still, all at the same time. This is the core of space adaptation sickness, the nausea and vertigo that afflict many astronauts during their first days in orbit. But even after this initial sickness subsides and the brain learns to ignore the most chaotic of these signals, a deeper disorientation remains. The subtle, ever-present sense of up and down is erased. When an astronaut closes their eyes to sleep, there is no gravitational anchor to provide a sense of stability. Many report a persistent low-level sensation of falling, a neurological ghost that haunts the edges of consciousness. The brain, deprived of its most fundamental spatial reference, remains in a state of high alert. How can you surrender to the vulnerability of deep sleep when some primal part of your mind is screaming that you're in a continuous, endless tumble through an infinite void? The relaxation required for slow-wave sleep becomes a neurological impossibility. Compounding this sensory confusion is the loss of proprioception. Strapped loosely inside a sleeping bag, floating in the middle of a module, the astronaut's body receives no pressure cues. There is no mattress signalling support to the muscles of the back and legs. There is no pillow cradling the head. This lack of physical feedback creates a proprioceptive void. The body's network of nerves, which constantly monitors muscle tension and limb position, has no external reference to confirm that it is safe to relax. Muscles that should be slack remain in a state of subtle, residual tension, as if perpetually waiting for an impact or a surface that will never arrive. The body never receives the all-clear signal to fully stand down, to enter that state of profound physical surrender that defines restorative rest. It remains on guard, a sentinel in the dark, unable to lay down its arms. And then there is the assault on the master clock itself. Aboard the International Space Station, orbiting the Earth at over 17,000 miles per hour, astronauts are hurled through 16 sunrises and 16 sunsets every 24 hours. The majestic planetary cycle of a light and dark that has wound our biological clocks for millions of years is replaced by a dizzying 90-minute strobe effect. The suprachiasmatic nucleus, bombarded with these rapid-fire, unnatural cues of day and night, becomes completely unmoored from reality. Its ability to conduct the body's hormonal symphony is shattered. The carefully timed release of cortisol and melatonin devolves into a chaotic mess. The body no longer has a clear internal signal for when to be alert and when to be drowsy. Astronauts often find themselves fighting overwhelming fatigue in the middle of a critical task, only to feel jarringly wide awake when their scheduled sleep period arrives. Mission planners try to impose a sense of terrestrial time with carefully managed lighting schedules inside the station, dimming the lights for night and raising them for day. But the cool, artificial glow of LED lights is a poor substitute for the full, rich spectrum of natural sunlight. It is like trying to conduct a symphony with a broken metronome in a soundproof room. The body's ancient rhythms, deprived of their planetary cues, begin to drift, desynchronize, and break down. This is the multi-front war that microgravity wages upon sleep. It is a physiological siege. The body is flooded by its own internal tides. The mind is lost in a sea of sensory confusion, cut adrift from its spatial anchor. The muscles are deprived of the very sensation of rest, and the ancient internal clock that has guided us through every night of our evolutionary history is shattered by the relentless orbital dawn. The result is a state of chronic sleep deprivation, a pervasive fatigue that degrades cognitive function, slows reaction times, and compromises the immune system, dangers that are magnified 1,000-fold in the unforgiving environment of space. The early astronauts discovered this brutal reality through exhausting first-hand experience. Their bodies, these magnificent products of Earth, were simply not built for this ethereal, weightless realm. They were strangers in a strange land, and their biology was in open revolt. The profound question that NASA and the world's space agencies now faced was not just a matter of comfort, but of survival. Faced with this fundamental rejection of sleep by the human body, how could we possibly fight back? How do you design rest for a body that has biologically forgotten what it feels like to be truly at rest? And so, the heroic age of orbital camping had to end. For decades, sleeping in space had been an exercise in improvisation, a clever hack managed with bungee cords and Velcro patches against a cold bulkhead. It was a temporary solution for a temporary presence, sufficient for missions measured in days or weeks. Astronauts were visitors, orbital tourists enduring the strangeness for a short while before the welcome return to the familiar embrace of Earth's gravity. But humanity's ambition was stretching, reaching for something far more profound than a fleeting visit. We weren't just going to space anymore, we were going to live there. This single shift in philosophy, from visitation to habitation, would change everything. The crucible for this new era was an unprecedented machine taking shape in the void, a sprawling multinational endeavour of gleaming modules and vast solar wings, the International Space Station. It was not a capsule or a shuttle, it was a home, intended to be permanently occupied. Suddenly, the old solutions were no longer good enough. The challenge was no longer how to survive a dozen nights of disjointed rest. The challenge was how to protect the human mind and body over hundreds, a ceaseless marathon of months turning into years, suspended in an environment for which we were never designed. The cumulative toll of imperfect sleep and annoyance on a week-long shuttle flight now loomed as a mission-critical threat on a 6-month expedition. Imagine the slow, creeping erosion of your focus, the persistent low-grade fatigue that dulls the razor's edge of your reflexes and clouds your judgment. In your office on Earth, this might lead to a spilled coffee or a missed deadline. Aboard a $200 billion orbital laboratory, travelling at 5 miles per second, a momentary lapse in concentration could be catastrophic. The constant, subtle disorientation, the lack of a true, deep restorative slumber, night after night for half a year, it was a physiological siege. The body's internal clock, the ancient circadian rhythm honed by millions of years of planetary rotation, was being held hostage by an orbital ballet of 16 sunrises and 16 sunsets every single day. The very concept of night and day had become an artificial construct, a schedule written on a mission clock, not a rhythm felt in the bones. The ad hoc straps and eye masks of the past were like trying to patch a dam with chewing gum. A fundamentally new approach was required, one rooted not in clever improvisation, but in deliberate human-centric engineering. The question was no longer, how do we keep astronauts from floating away while they sleep? The question had become, how do we build a bedroom in the void? How do we construct a sanctuary for the mind in the most alien environment humanity has ever known? This paradigm shift gave birth to one of the most deceptively simple, yet brilliantly complex pieces of hardware on the ISS. the personal crew quarters. These were not mere sleeping nooks. They were the first true bedrooms in space. On a station where every cubic centimetre is meticulously planned and multifunctional, the decision to dedicate entire private compartments purely for rest and personal time was a revolutionary acknowledgement of human need. Each of these compartments, roughly the size of a telephone booth, represented a cocoon of terrestrial familiarity. Step inside, and you would find yourself in a space engineered to fight the chaos of orbit. The walls were not bare metal, but lined with sound-dampening materials. The ISS is a living, breathing machine, a place of perpetual noise. It's a symphony of whirring fans, clicking relays, and humming pumps from the life support systems. A constant low-level hum that, without insulation, would seep into an astronaut's consciousness and forbid the deep silence required for true rest. The crew quarters were designed as acoustic islands, sanctuaries where that ever-present mechanical drone could finally fade away. Within this quieted space, the environment could be controlled with a precision impossible in the station's larger, shared modules. An astronaut could seal the hatch and plunge their world into absolute darkness, an essential tool for convincing a confused endocrine system that it was, indeed, time to sleep, regardless of the searing sunlight blazing past the window just a few feet away. This was a circadian fortress, a place where the tyranny of the orbital day could be held at bay. Yet the most critical engineering challenge lay within the very air they breathed. Here on Earth, when you exhale, the warmer, carbon dioxide-rich air naturally rises away from your face through convection. In microgravity, convection is a dead concept. There is no up for hot air to go. An astronaut sleeping soundly in a sealed space without proper airflow would quickly become enveloped in a bubble of their own exhaled CO2. They would wake up gasping for air, suffering from headaches, their sleep poisoned by the very act of breathing. To solve this, each crew quarter is equipped with its own dedicated ventilation system, a constant, gentle current of air directed across the sleeping area, a man-made breeze that perpetually sweeps away the dangerous carbon dioxide and ensures a steady supply of fresh, oxygenated air. It is an invisible, life-sustaining river flowing through the night. But these spaces were designed for more than just the body. They were built for the soul. For the first time, an astronaut had a truly private space, a door they could close. A place to pin photos of their family, to float with a laptop and write an email home, to listen to music without headphones, to simply be alone with their thoughts, utterly shielded from the eyes and ears of their crewmates and the ever-watchful gaze of mission control. This tiny booth of privacy was a powerful psychological anchor, a vital defense against the immense pressure of living and working in a confined space with the same small group of people for months on end. It was the one place on the station, and perhaps in the entire cosmos, that was truly theirs. And at the heart of this personal sanctuary was the sleep bag. To call it a simple sleeping bag is to do it a profound disservice. It is a meticulously engineered micro-environment, a wearable habitat designed to trick the human body into a state of rest. Affixed vertically to one of the walls, since orientation is meaningless, the bag is a testament to thousands of hours of research into physiology and psychology. The material itself is a marvel, a fire-retardant, breathable fabric that is soft to the touch yet incredibly durable. But its true genius lies in its internal architecture. Simply floating freely inside a loose bag would still leave an astronaut feeling exposed, untethered, their limbs drifting into awkward positions. To counteract this, the sleep bag features a system of soft, elastic restraints inside. These are not rigid harnesses, but gentle tethers that provide a subtle, constant pressure against the body. When an astronaut is zipped inside, these restraints press against their back, their legs, their shoulders. The effect is transformative. It is a phantom caress of gravity. For a body that has spent its entire evolutionary history feeling the press of a mattress, the weight of a blanket, this gentle, distributed pressure is a powerful neurological cue. It tells the deep primal parts of the brain that it is safe, secure, and held in place, allowing the muscles to finally relax in a way that free-floating simply does not permit. It is a simulation of the comforting weight that we all associate with lying down to sleep, a ghost of the bed we left behind on our home planet. The design accounts for every human subtlety, Armholes are built into the sides, allowing an astronaut to comfortably work on a laptop or read a book before turning in, their arms free while the rest of their body remains securely anchored. At the top, a cushioned but firm head restraint serves as a phantom pillow. The head doesn't need support in zero-G. It weighs nothing. But the mind expects it. The feeling of something gently cupping the back of the head is another powerful psychological signal, a final piece of the terrestrial puzzle that helps initiate the cascade of brain chemistry leading to sleep. An astronaut preparing for bed on the ISS engages in a ritual that is both strangely alien and deeply familiar. They float into their private quarters, seal the hatch on the bustling station, and dim the lights. They slide into the sleep bag, feet first, zipping it up to their neck. They secure the inner tethers, feeling that gentle, reassuring pressure envelop them. They might put on headphones, listening to the sounds of a rainforest or ocean waves to further mask the station's hum. In that moment, cocooned within their soundproofed, darkened, perfectly ventilated chamber, held by the phantom gravity of their sleep restraint, they are as close to a bedroom on Earth as human ingenuity can provide. They are no longer just a body in a machine. They are a person in their room preparing for a night's rest. Waking up, however, can still be a moment of profound confusion. For a fleeting instant upon opening your eyes before the conscious brain fully engages, you have no idea which way is up. The inner ear, your biological gyroscope, offers no clues. You see a wall in front of you with your laptop attached, but is it a wall or is it the floor? Is the ceiling above you or is that another wall? It is a moment of pure, unadulterated spatial anarchy. Then, memory kicks in. You remember you're not on Earth. You're on the International Space Station. You're in your sleep bag, tethered to the wall of Node 2. And with a push of your fingertips, you glide out of your cocoon and into the new day, ready for the complex work ahead. Your mind and body restored not by accident or by luck, but by one of the most thoughtful and critical acts of engineering in human history. This deliberate focus on creating a habitable sleep environment has paid enormous dividends. Data collected from decades of ISS expeditions shows a clear correlation between the quality of these engineered sleep stations and astronaut performance. Crew members report better sleep, improved mood, and higher cognitive function compared to the experiences of their predecessors on Mir or Skylab. The science of sleep in space became a field of study in its own right, with the ISS serving as the ultimate laboratory. Astronauts participate in experiments, wearing sophisticated monitoring equipment that tracks brain waves, heart rate, and body movement throughout the night. This data is beamed back to Earth, analysed by sleep specialists who are piecing together the subtle and complex ways that long-term microgravity and the unique orbital environment alter the very architecture of our sleep. We are learning that even with these incredible tools, space sleep is different. Astronauts often experience a reduction in the deepest, most restorative stages of sleep, known as slow-wave sleep. Their REM cycles, where we do our most vivid dreaming, can be fragmented. The dreams themselves are often reported to be intense, disorienting flights of fancy, the brain trying to make sense of its bizarre, gravity-free existence. The development of the crew quarters and sleep bags was not an endpoint. It was not the final solution to the problem of sleeping in space. Rather, it was a magnificent achievement that allowed us to climb to a new plateau of understanding. By solving the most immediate physically disruptive problems, the drifting, the noise, the light, the CO2 build-up, we cleared the way to see the deeper, more insidious challenges that lay beneath. We had successfully built a bedroom in the void, a remarkable feat of engineering and human empathy. We had transformed sleep from an acute survival challenge into a manageable aspect of daily life in orbit. But in doing so, we uncovered a whole new continent of questions. We now knew that we could keep an astronaut comfortable, but could we truly keep them healthy? We had provided a sanctuary for the body, but what were the long-term consequences for the brain, for the very essence of human consciousness, when it is untethered from its homeworld for years at a time? The success of the ISS sleep systems proved that we could live in low Earth orbit, but it also revealed the profound biological and neurological hurdles we would have to overcome if we were to ever push outward, to leave this cradle entirely and begin the long, dark journey to Mars. The problem was far from solved. It had just become infinitely more interesting. So we had conquered the physics of slumber in a world without weight. We had learned to anchor ourselves against the void, to create personal cocoons of quiet darkness amidst the stars, transforming a disorienting freefall into a serene, almost dreamlike repose. For a time, it seemed the problem was solved, another testament to human ingenuity. But the universe rarely offers such simple victories. Beyond the elegant mechanics of tethers and sleep sacks, a far more insidious set of challenges began to emerge, problems not of physics, but of deep biology and the very wiring of the human mind. The initial triumph gave way to a persistent, grinding struggle, a long downward path paved not with overt dangers, but with the subtle, cumulative poisons of an environment fundamentally alien to our terrestrial design. The International Space Station, our magnificent outpost in the heavens, revealed itself to be a profoundly difficult place to find true, restorative rest. It turns out you can take the human out of the Earth, but you cannot so easily take the Earth out of the human. The first hint of this deeper complexity isn't something you see, but something you hear, or rather, something you can never escape hearing. From the moment you float through the hatch, you are enveloped in a constant, omnipresent hum. It is the sound of life itself, the ceaseless thrum of the machinery that keeps you alive. The fans of the environmental control and life support system, the pumps circulating coolant, the whirring of experiments, the clicks of relays, all of it merges into a single monotonous auditory fog. It's a soundscape that has been measured at between 60 and 70 decibels, roughly equivalent to the noise of a vacuum cleaner running in the next room. Forever. There is no door to close, no window to shut. There is no night that brings with it the quiet stillness of a terrestrial evening. There is only the machine, the relentless mechanical heartbeat of the station, a sound that bores its way into your consciousness and most critically into your sleep. Astronaut Scott Kelly, who spent nearly a year in this environment, described it as a constant presence you must actively, consciously learn to ignore. Your brain, evolved over millennia to interpret sound as a signal, a sign of opportunity or a warning of danger, is suddenly submerged in an ocean of meaningless yet unceasing noise. During the day, this auditory backdrop can be relegated to the periphery of your focus as you work, but at night, when the mind seeks sanctuary, the hum becomes a predator. It prowls the edges of sleep, preventing the deep, profound relaxation necessary for the brain to truly disengage. Sleep studies conducted on the ISS have revealed that astronauts experience significantly less deep-wave sleep, the most restorative phase, compared to their time on Earth. Their brains simply refuse to fully power down, perpetually held in a state of low-level vigilance by the station's unyielding murmur. It's like trying to sleep at a loud, unending party where the music never fades. Some astronauts use earplugs, others noise-cancelling headphones, but these are mere barricades against a tide. The low-frequency vibrations travel through the very structure of the station, through the walls of your sleep pod, through your pillow, a subtle, resonant tremor you feel in your bones. It is the restless ghost in the machine, a constant reminder that your life and your sleep are entirely dependent on its flawless, noisy operation. If the auditory environment is a relentless assault, the visual one is a profound betrayal of biological expectation. Our bodies are exquisite timepieces, calibrated over eons by the simple, reliable rhythm of a rising and setting sun. This internal clock, our circadian rhythm, is governed by a tiny cluster of neurons in the brain called the suprachiasmatic nucleus. It dictates nearly every aspect of our physiology, from hormone release to body temperature to our cycles of sleepiness and wakefulness. And its primary external cue, the master gear that sets the entire clockwork in motion, is light. Specifically, the changing quality and quantity of light throughout a 24-hour period. The ISS, however, orbits the Earth at over 17,000 miles per hour, completing a full circuit every 90 minutes. This means its inhabitants witness 16 sunrises and 16 sunsets every single day. The sublime, poetic spectacle you might imagine quickly becomes a source of deep biological confusion. Imagine closing your eyes to sleep, only to have the brilliant, unfiltered glare of the sun blast through your window 45 minutes later. The station's designers understood this problem, of course. The windows in the crew quarters are fitted with thick, multi-layered shutters to create an artificial night. But the problem of light is more pervasive than that. Inside the station, the lighting is entirely artificial, a synthetic daylight designed to keep the crew alert and productive during their long working hours. For years, this lighting was provided by fluorescent bulbs that emitted a broad spectrum of light, including a significant amount of blue light. We now know that the photoreceptors in our eyes are exquisitely sensitive to this blue wavelength. When they detect it, they send a powerful signal directly to the brain's master clock. It is daytime, wake up, suppress the production of melatonin. Melatonin is the hormone of darkness, the chemical messenger that tells your body it is time to power down and prepare for sleep. Bathed in the persistent blue-tinged glow of the station's interior for 16 hours a day, an astronaut's brain is in a state of perpetual daylight. The scheduled night on the ISS is an arbitrary declaration, a time agreed upon by mission control. At the designated hour, many of the main lights are dimmed or switched off, and the crew retreats to their sleep stations. But the biological signal has already been sent and the damage done. Melatonin production has been blunted, the internal drive for sleep weakened. It's an invisible form of jet lag from which there is no escape, a journey across 16 time zones every hour and a half. Astronauts have described the peculiar sensation of feeling physically exhausted from a hard day's work, yet their minds remain stubbornly, frustratingly awake. They lie in their sleeping bags, anchored in the silent dark of their pods, but their brains are still humming with the ghost of the artificial sun. This disruption goes beyond mere tiredness. It throws the body's entire regulatory system into disarray. Studies have shown it can impact immune function, cognitive performance, and mood. The quest to engineer the perfect artificial day to maintain peak performance had inadvertently created the perfect conditions for a deeply compromised night. It was a classic case of a solution for one problem, creating a cascade of new, more subtle complications for another, demonstrating just how intricately our biology is tethered to the planetary rhythms we left behind. And then there is the weight that cannot be measured on any scale, the gravity of the mind itself. Living on the International Space Station is not a vacation. It is one of the most demanding, high-stakes jobs in human history. You are living and working in the same confined space, a complex labyrinth of modules and machinery, with the same handful of colleagues for 6 months or more. Your every moment is scheduled, your every action monitored. You're a multi-million-dollar national asset, conducting complex scientific experiments where a single mistake could ruin years of research. You're a mechanic, a scientist, a doctor, and a janitor, all while maintaining the physical fitness required to counteract the brutal effects of microgravity on your body. The pressure is immense. There is no going for a walk to clear your head. There is no true privacy, no genuine escape from the demands of the mission or the social dynamics of your small, isolated tribe. This psychological pressure is a powerful antagonist to sleep. The human brain is not designed to switch off on command, especially when it is preoccupied with the next day's critical robotics maneuver or worrying about a family issue back on a planet you can see but cannot touch. Many astronauts report a phenomenon known as sleep displacement, where they find themselves lying awake, mentally rehearsing procedures for the following day, unable to disengage their hyper-vigilant, mission-focused minds. The very traits that make them exceptional astronauts, their meticulous attention to detail, their relentless drive for perfection, their ability to think 5 steps ahead, become liabilities when their heads hit the pillow. The silence of their sleep pod becomes a theatre for their anxieties and responsibilities. This psychological burden intertwines with the physiological stresses in a destructive feedback loop. The constant noise and disrupted light cycles degrade sleep quality, leading to fatigue. Fatigue can impair cognitive function and heighten emotional reactivity, making it harder to cope with the psychological pressures of the mission. The increased stress and anxiety in turn make it even more difficult to fall asleep. It becomes a vicious, downward spiral. Faced with this relentless combination of auditory, biological, and psychological assault, it is unsurprising that many astronauts have turned to pharmacology for help. The use of sleep aids, from over-the-counter antihistamines to prescription medications like Ambien or Sonata, is common on the ISS. NASA has, over many years, carefully studied and approved a specific formulary of medications for in-flight use. This is not a decision taken lightly. Any medication carries risks, and these are amplified in the unique environment of space. How does a drug metabolize differently in microgravity? What are the next-day cognitive side effects, the so-called sleep hangover, when you're responsible for operating a complex piece of machinery worth billions of dollars? Astronauts must meticulously log any medication they take, and there are strict protocols. But the reality is that for many, these pills become a necessary tool, a chemical switch to override a system that simply refuses to power down on its own. It is a pragmatic, if imperfect, solution to a debilitating problem. One veteran astronaut recounted the nightly ritual, a choice between two undesirable outcomes. He could either lie awake for hours, his mind racing, knowing that his exhaustion the next day would compromise his work and potentially endanger the mission, or he could take a pill that would grant him a few hours of chemically induced unconsciousness, hoping the residual grogginess would wear off before his most critical tasks began. This is the hidden toll of our grand endeavour. For every stunning photograph of the Earth from orbit, for every groundbreaking scientific discovery, there is the untold story of the human being who, night after night, fights a private, silent battle for a few precious hours of genuine rest. The reliance on sleep aids is a stark admission of our biological limitations. It signals that despite all our technological prowess, we have not yet built a true home in space. We have built a magnificent, life-sustaining machine, but we are still learning how to live inside it, how to convince our ancient, earth-tuned bodies that this humming, brightly lit vessel hurtling through an endless night is a safe place to close our eyes and truly let go. This persistent, nagging problem of sleep is more than just an inconvenience. It represents one of the most significant and complex human challenges we face. It proves that the greatest distances we must travel are not merely the millions of miles to other worlds, but the infinitesimal, yet profound gaps in understanding our own biology and psychology. And as we set our sights on longer, more ambitious missions to the Moon, to Mars, and beyond, solving this fundamental human need is no longer just a matter of comfort or performance, it is a matter of survival. And so, the brutal calculus of spaceflight demanded a revolution. Not of propulsion or of shielding, but of the very architecture of rest itself. The old model, the one that treated sleep as a mere biological necessity to be crammed into the mission plan, had been proven a dangerous failure. A new philosophy was taking hold, one born from decades of exhaustion and error, a philosophy that recognized a rested mind is the most critical mission hardware of all. We had learned, through bitter experience, that you cannot simply command a human being to sleep in an environment so profoundly hostile to it. You must instead persuade the body, coax the mind, and create an illusion of home in the heart of the void. You have to build a sanctuary. This sanctuary begins not with grand engineering, but with a humble puff of air. Inside the crew quarters, or sleep stations, of the International Space Station, a subtle but constant battle is waged against an invisible enemy, your own breath. In the absence of gravity, the warm carbon dioxide-rich air you exhale doesn't rise and dissipate. It lingers, forming a silent, stagnant cloud around your head. Early astronauts would often wake with a gasp, a pounding headache, and a desperate feeling of suffocation, their bodies starved for oxygen. The solution was an elegant piece of fluid dynamics, a ventilation system designed to generate a gentle, continuous stream of air across the astronaut's face. It isn't a gale force wind, but a precisely calculated current, a ghost of a terrestrial breeze. This microclimate, this personal whisper of wind, carries away the carbon dioxide, ensuring every breath is fresh and clean. It's the first, most fundamental promise the environment makes to the sleeping mind. Here, you can breathe easy. Here, you're safe. Then, there is the matter of the noise. We imagine space as silent, but the inside of a space station is a perpetual factory floor. For 24 hours a day, it is a symphony of machinery, a complex orchestra of survival, the ceaseless hum of life support systems, the whir of cooling fans, the sudden clank of a pump engaging, the crackle of communications. This is the station's heartbeat, and it never stops. To sleep through it is like trying to nap on an aircraft carrier's flight deck. The modern sleep station, therefore, is an acoustic fortress. Its walls are lined with advanced sound-dampening materials born from stealth submarine technology, designed to absorb and deaden the relentless vibrations that travel through the station's metallic skeleton. But passive measures are not enough. Inside, a sophisticated white noise generator can be activated, not just masking the external clamour, but creating a smooth, predictable soundscape. It's a sonic blanket, allowing the brain's vigilant sentinels to finally stand down, secure in the knowledge that no sudden, jarring noise will signal a non-existent emergency. With the air clean and the world quieted, the final physical barrier to sleep is light. In orbit, the sun is not a gentle, distant friend. It is a celestial blowtorch that appears and disappears 16 times a day. These abrupt, searing sunrises can slice through an astronaut's closed eyelids, jolting their brain into a state of alert. The sleep station's hatch is therefore more than a door. It's an armoured light shield. It seals with absolute perfect darkness. No stray photons from a colleague's late-night work or a flash of sunlight from a passing window can penetrate this personal night. Yet, paradoxically, the greatest innovation in managing the light is not in how it's blocked, but in how it's meticulously introduced. For we have learned that the key to mastering sleep in space is to become the masters of our own internal clocks. This is where human ingenuity transcends mere comfort and enters the realm of chronobiology. We now understand that the human circadian rhythm is a deeply ancient mechanism, a fragile dance conducted by a tiny cluster of neurons in the hypothalamus. It is a rhythm that expects, that needs, the predictable cadence of a terrestrial day to keep time. Take that away, and it drifts, it stumbles, it falls into chaos. For years, we fought this drift with pharmacology, with sleeping pills that offered a crude chemical imitation of rest, often leaving astronauts groggy and disconnected. The true breakthrough came when we stopped trying to bludgeon the body clock into submission, and instead learned to speak its language. And the language of the circadian rhythm is light. Inside the station, a revolution in solid-state lighting has been unfolding. Arrays of precisely tuned LEDs have been installed, capable of producing light across the entire visible spectrum. This is not just illumination. This is a form of biological programming. In the morning, astronauts are bathed in intense blue spectrum light. This specific wavelength, around 480 nanometers, is a powerful signal to the brain's master clock. It screams daytime more effectively than any alarm. It suppresses the production of melatonin, the hormone of darkness, and triggers a cascade of the neurochemicals that promote alertness, focus, and cognitive performance. It is, in effect, a digital sunrise painted onto the astronauts' retinas, capable of anchoring their drifting biological clock to the mission schedule with pinpoint accuracy. You can watch an astronaut's entire demeanour change as the blue light intensifies, their movements becoming sharper, their minds more engaged. Then, as their designated day draws to a close, the lightscape of the station performs a slow, deliberate transformation. The harsh blues and bright whites begin to fade, replaced by a warm, gentle wash of amber and red hues. This shift to the longer wavelengths of the spectrum is a carefully orchestrated signal to the body that the day's work is done. This reddening of the environment actively prevents the suppression of melatonin. The brain, sensing this artificial twilight, begins the ancient process of preparing for sleep. Melatonin levels rise, core body temperature starts to drop, and a feeling of gentle drowsiness begins to set in. We are no longer leaving the circadian rhythm to fend for itself in a sea of temporal confusion. We have become its conductors, its choreographers, using light as our baton to orchestrate a perfect 24-hour cycle of wakefulness and rest, completely independent of the chaotic solar cycles raging just outside the hull. This level of control allows for unprecedented personalization. Before a mission, astronauts undergo extensive chronotyping, a deep analysis of their unique individual body clocks. Are they a lark, naturally inclined to wake and sleep early, or an owl with a biological preference for later hours. This data is used to create a bespoke lighting schedule for each crew member, downloaded to their personal devices and integrated with the station's main lighting system. One astronaut's sleep station might begin its gentle simulated sunrise at 0600 Greenwich Mean Time, while their crewmate, a natural night owl, might receive their wake-up call of blue light a full hour later. This tailored approach acknowledges a profound truth. There is no single, universal human. Our biology is personal. By honouring these deep-seated individual rhythms, we not only improve sleep but also enhance mood, teamwork, and mission effectiveness. The days of a one-size-fits-all schedule are over, replaced by a symphony of individualised biological management. But light is only one part of the equation. The body must also be convinced through physical exertion. In the frictionless world of microgravity, muscles atrophy and bones lose density. The vigorous exercise regimes astronauts undertake, 2 hours every single day, were designed primarily to combat this physical decay. Yet we've discovered a powerful secondary benefit directly linked to sleep. Pushing against the powerful pneumatic resistance of the Advanced Resistive Exercise Device, or ARED, or running for miles on a specially designed treadmill doesn't just maintain physical health, it tires the body in a way that floating never can. This intense physical stress creates a deep physiological need for recovery, for the restorative processes that happen only during the profound slumber of deep, slow-wave sleep. The exercise is a gravitational anchor for the metabolism. It elevates core body temperature, which then naturally drops several hours later, a key trigger for sleep initiation. It releases endorphins, which can elevate mood and reduce the stress that so often inhibits rest. And it consumes energy, creating a genuine cellular-level fatigue. Astronauts report that after a grueling workout session, their bodies feel a familiar terrestrial weightiness, a longing for rest that the constant, effortless motion of floating had stolen from them. They are, in essence, forging sleep from iron and sweat. This daily ritual of intense physical effort has become one of the most reliable, non-pharmacological sleep aids available in orbit, a way of reminding the body of its earthly limits, and in doing so, reminding it of its deep need for recovery and peace. Beyond the physical and the environmental, the final frontier of sleep in orbit has been the mind itself. Even with perfect air, perfect silence, and perfect light, an anxious mind can refuse the call to rest. The psychological pressure of spaceflight is immense, the isolation, the constant awareness of risk, the demanding pace of scientific work. To address this, space agencies have integrated sophisticated behavioral strategies into astronaut training, tools for navigating the inner cosmos. Cognitive behavioral therapy for insomnia, or CBTI, has proven remarkably effective. Astronauts learn to break the cycle of anxious thoughts about sleep, reframing their relationship with their sleep station not as a place of struggle, but as a place of rest. They learn relaxation techniques, mental exercises that can calm a racing heart and a preoccupied mind. Increasingly, ancient contemplative practices are finding their place alongside this cutting-edge technology. Guided meditation and mindfulness exercises are now available on crew iPads, providing a powerful tool for disengaging from the day's stresses. Floating in their darkened sleep sack, an astronaut can listen to a calming voice that guides them to focus on their breath, to notice the subtle sensations of their body, to let go of the mission checklist and simply be present. It is a profound act of finding the quiet center in the orbital storm. These techniques empower the astronauts, giving them agency over their own mental state. They are no longer passive victims of their environment, but active participants in creating their own internal peace. The result is a more resilient, focused, and psychologically robust crew, capable of handling the immense pressures of their job because they have been given the tools to consciously and deliberately find rest. The culmination of these efforts, the engineered environment, the biological programming through light, the physical preparation through exercise, and the mental resilience through behavioral training, represents a paradigm shift. We have finally created a holistic system, a multi-layered approach that honors the complexity of the human organism. We are now able to gather more data than ever before, Wearable sensors, much like those you might use on Earth, track an astronaut's sleep stages, heart rate variability, and body temperature. This data is downlinked, analysed, and used to make micro-adjustments to their light exposure, their exercise intensity, or even their dietary intake. Sleep has been transformed from a nightly gamble into a manageable, optimizable aspect of mission performance. The change in the astronaut experience is palpable. You can hear it in their voices during interviews from orbit. The exhaustion and irritability that marked so many early missions have been replaced by a vibrant energy. They speak of waking up feeling truly refreshed, of having vivid dreams again, a sign of healthy, REM sleep that was often suppressed in the past. They describe the profound psychological comfort of their personal sleep station, their one truly private space in a world of constant observation and shared living. It is their cave, their nest, their small patch of Earth in a sea of stars. This triumph is not merely about comfort, it is the critical enabling factor for the future of human exploration. A well-rested crew is a safe crew. A well-rested crew is an effective crew. And as we set our sights on destinations far beyond the cradle of Earth orbit, on long-duration missions to Mars and beyond, the lessons learned in the sleepless nights aboard the ISS will be our guide. For we now know that to conquer the vast emptiness of outer space, we must first learn how to conquer the intricate universe within ourselves, mastering the simple, sacred, and essential act of sleep. And so, within these orbiting laboratories, the battle for rest is waged not with brute force, but with light, with chemistry, and with an intimate, evolving understanding of the human machine. The meticulously calibrated spectrum of the station's solid-state lamps, the careful scheduling of tasks, the precise monitoring of an astronaut's core temperature and melatonin levels. These are the modern tools in a struggle as old as our dreams of flight. They represent the culmination of decades of trial and error, a hard-won peace treaty signed with the disorienting void. Yet, to truly appreciate the sophistication of this nightly ritual, we must cast our minds back through the silent decades to the pioneers. We must remember the first restless nights when humanity, for the first time, untethered itself from the gentle, persistent pull of home. Imagine the earliest cosmonauts and astronauts, true explorers in every sense, adrift in their tiny tin can capsules. For them, sleep was not a managed process, but a chaotic surrender. Stripped of the primordial comfort of gravity, that constant reassuring pressure that has defined life for 3.5 billion years, their bodies were in open rebellion. The inner ear, our internal gyroscope, spun wildly without a clear signal of down, sending waves of nausea and vertigo through their systems. Fluids, no longer pooled in their legs, drifted upward, creating a relentless pressure in their heads, a perpetual sensation of hanging upside down that no amount of conscious effort could dispel. They were pioneers adrift on an ocean of nothingness, their sleep punctuated by the unnerving freedom of a floating limb, the cold shock of a drifting tool bumping against a wall in the dark. They were learning, in the most visceral way possible, that leaving Earth meant leaving behind the very anchors of our biology. This journey, from those first disoriented slumbers to the managed tranquility of the International Space Station, is more than just a story about sleep. It is a perfect microcosm of our entire adaptation to living in space. Every challenge we face in the cosmos, from muscle atrophy and bone density loss to psychological strain and radiation exposure, is mirrored in this nightly quest for repose. To solve the problem of sleep, we had to first understand the profound ways in which the absence of gravity rewrites the fundamental rules of human physiology. We had to become masters of our own internal environment, because the external one was so uncompromisingly hostile. The sleeping bag tethered to the wall was not merely a bed, it became a symbol of our refusal to be perpetually adrift. The eye mask was not just for blocking light, it was a shield against the disorienting 24-hour cycle of 16 sunrises and sunsets. Learning to sleep in space was, in essence, learning to create a portable piece of Earth. It was an act of profound biological and psychological engineering. We had to trick the body into feeling a sense of security it had no right to feel, floating in a vacuum at 17,500 miles per hour. We had to command the circadian rhythm, that ancient internal clock wound by the turning of our planet to obey a new master, a digital schedule beamed from mission control. This was our first, and perhaps greatest, act of extraterrestrial colonization. Not the planting of a flag on a distant world, but the successful establishment of a sustainable, internal human ecosystem far from the cradle of our evolution. The quiet, rhythmic breathing of a sleeping astronaut aboard the ISS is the sound of victory, a testament to our species' remarkable, stubborn adaptability. It's a quiet declaration that wherever we go, we will find a way to make a home, even if that home is just the few cubic feet of personal space where we can safely close our eyes and dream. But our journey is far from over. The relative comfort of low Earth orbit, our celestial backyard, has been a magnificent training ground. It has taught us the essential lessons of survival. Now, however, we are lifting our gaze, looking beyond this orbital sanctuary, toward destinations that will test our adaptability in entirely new ways. We are returning to the moon, not for fleeting visits of days, but to build a lasting presence, a stepping stone into the deeper solar system. And after the moon, the great red prize awaits, Mars. These worlds will not present us with the simple absence of gravity. They will introduce a far more subtle and potentially more complex challenge. They will confront us with the persistent, unrelenting strangeness of partial gravity. On the moon, you will not float, but you will not truly walk either. You will be bound by 1/6 of the Earth's gravitational pull, a gentle tether that is neither here nor there. How will the human body, so finely tuned to the full, reassuring embrace of 1G, respond to this ghostly whisper of gravity during its most vulnerable hours? The fluid shifts that cause sinus pressure and headaches in orbit might be lessened, but they will not vanish. The inner ear may find a faint sense of down, but will it be enough to quell the vestibular confusion that plagues new spacefarers? The very architecture of sleep, the delicate dance between light sleep, deep restorative sleep, and the rapid eye movement of our dreaming state, could be fundamentally altered. We have no data on how a human being adapts to sleeping for months on end in a 1/6 G environment. The challenges are as practical as they are physiological. Will lunar astronauts still need to be zipped into sleeping bags? Or will the gentle pull be enough to keep them anchored to their bunks? A floating arm might no longer wake you, but what of the slow, gentle, disquieting drift of your entire body if you shift in your sleep? The dust on the moon, a fine abrasive powder of razor-sharp silicate shards called regolith, will be a constant threat. It will cling to everything, and the slightest contamination within a habitat could lead to severe respiratory and eye irritation, making restful sleep an impossibility. Habitats will need to be designed with meticulous air filtration and dust mitigation systems, creating a clean sanctuary against the hostile lunar surface. Furthermore, the lunar day and night cycle is punishingly long, over 2 weeks of continuous searing sunlight, followed by 2 weeks of frigid, absolute darkness. This completely obliterates the 24-hour rhythm our bodies crave. The artificial lighting systems pioneered on the ISS will need to be even more sophisticated, not just mimicking a terrestrial day, but actively fighting against the monolithic, month-long cycle of the moon itself, becoming an umbilical cord of a light connecting the crew's biology back to the distant memory of an earthly day. The lunar habitat, whether on the sun-scorched surface or nestled within the protective shelter of a lava tube, will be the next great laboratory for human sleep. We will have to relearn the basics, collecting new data on brainwaves, heart rates, and hormonal fluctuations in this in-between gravitational state. We will need to design sleep stations that perhaps offer a slight constant pressure, simulating the feeling of a mattress to trick the body's proprioceptive senses into a deeper state of relaxation. The moon will be our proving ground, the place where we determine if humanity can truly adapt to living long-term on another celestial body. And every lesson learned in the stark, silent landscape of the Sea of Tranquility will be absolutely critical for the next, far more ambitious leap. Because the journey to Mars will push the human mind and body to their absolute limits, and the simple act of sleeping will become one of the most critical mission parameters of all. The voyage to Mars is a chasm of time and distance. For 6 to 9 months, a small crew will be sealed inside a vessel, a tiny spark of life crossing the immense dark void between worlds. Earth will shrink from a vibrant, swirling blue marble to a brilliant, star-like point of light, its familiar day-night cycle becoming a distant abstraction. The psychological strain of this isolation will be immense, a pressure cooker for interpersonal conflicts and mental fatigue. In this environment, sleep is not a luxury. It is the essential maintenance procedure for the human mind. Without consistent, high-quality rest, cognitive function degrades, reaction times slow, and emotional regulation frays. A sleep-deprived astronaut is a danger to themselves and to the entire mission. The schedules will have to be ironclad, the sleep chambers engineered to be sanctuaries of perfect calm, isolated from the hum of machinery and the inevitable tensions of a long-duration flight. But the challenges go deeper than just scheduling. The tyranny of the sun, which governs our lives on Earth, will be replaced by the tyranny of the mission clock. The crew's circadian rhythms will be completely unmoored from any natural celestial cycle. Mission planners are already exploring radical solutions. Perhaps the spacecraft itself will become a temporal bubble, with lighting systems that don't just mimic a 24-hour Earth day, but a slightly longer one, a 24.6-hour sol, to begin pre-acclimatizing the crew to the length of a Martian day before they even arrive. This would be an attempt to wind their internal clocks forward, a slow, gentle preparation for the new world awaiting them. Failure to manage this desynchronization could lead to a pervasive, mission-threatening fatigue, a cosmic jet lag from which there is no easy recovery. And then there is the radiation. Beyond the protective embrace of Earth's magnetic field, space is saturated with an invisible high-energy rain of galactic cosmic rays and solar particles. On the journey to Mars, astronauts will be exposed to radiation levels hundreds of times higher than on Earth. This is not just a long-term cancer risk, it has immediate tangible effects. Astronauts on the ISS have reported seeing strange flashes of light, even with their eyes closed. These are thought to be charged particles striking the optic nerve or the visual cortex of the brain, a direct physical intrusion of the cosmos into their consciousness. Imagine trying to drift off to sleep while your own brain serves as a particle detector, with streaks and bursts of light randomly piercing the darkness behind your eyelids. To sleep safely on the way to Mars, and indeed on Mars itself, crews will need heavily shielded havens. The sleep stations on the transit vehicle might be located in the core of the spacecraft, surrounded by water tanks, food supplies, and even the crew's own waste products. Anything with mass that can help absorb this relentless bombardment. On the Martian surface, the situation is even more dire. With its thin atmosphere and lack of a global magnetic field, Mars offers little protection. The first Martian explorers will likely live and sleep underground. They may inhabit inflatable structures buried beneath several meters of Martian soil, or find shelter in natural lava tubes. Their bedrooms will be caves, bunkers designed to shield their vulnerable, sleeping bodies from the constant threat of radiation. The psychological implications are profound. To find rest, humanity will have to burrow into the very planet it seeks to explore, becoming a subterranean species by necessity. Sleep on Mars will be an act of seeking refuge, of retreating from the beautiful but deadly surface into a protected burrow. And what of Martian gravity? At 38% of Earth's, it is a more substantial anchor than the Moon's, yet it remains a profoundly alien environment. Over a mission lasting years, how will the body respond to sleeping in this 1/3 gravity? Will the fluid shift still be a problem? Will the cardiovascular system, no longer having to work as hard to pump blood uphill, decondition in ways that affect sleep quality? Will the musculoskeletal system, under a lighter load, ever truly relax in the way it does on Earth? These are not trivial questions. The answers will determine the long-term health and effectiveness of any human presence on Mars. The first Martian habitat will need a sophisticated medical bay capable of conducting detailed sleep studies, turning the first explorers into research subjects in the greatest biological experiment ever undertaken. They will be charting the unknown territory of the human body's limits, and their sleep logs will be as vital as any geological survey or atmospheric sample. From the first confused tumbling in a Vostok capsule to the dream of a shielded cavern on Mars, our quest to sleep among the stars charts the very course of our ambition. it reveals a fundamental truth about exploration. It is not enough to simply arrive at a new world. We must be able to live there. We must be able to endure. And to endure, we must be able to rest. The simple, nightly act of surrender we take for granted on Earth becomes, in the cosmos, a complex and vital science. It is the bedrock of mental health, the foundation of peak performance, and the very measure of our ability to adapt. The future of human space exploration, our dream of becoming a multiplanetary species, may ultimately depend not on the power of our rockets or the speed of our computers, but on our ability to solve this most basic, most human of needs. We are learning to carry the quiet, restorative peace of an earthly night with us, a cosmic lullaby engineered from science and sheer determination. As we push farther into the great silent darkness, our greatest challenge will be to find, again and again, a safe harbour where we can close our eyes, feel the ghost of gravity's embrace, and dream of the worlds we have yet to conquer.